In this demonstration, we present ASM, a cardinality estimator that utilizes autoregressive models, sampling, and multidimensional statistics merging, which outperforms the previous state-of-the-art method factor join by up to 270 times. We showcase the internal estimation process of ASM and compare its performance with other alternatives. To do this, we simulate a scenario where a DBA wants to analyze and enhance query plans. The DBA first issues a registered benchmark query or their own query from one of the three databases, IMDb, StatsCAB, or STAC. The DBA chooses the JOB13B query and all the estimators to view plans and execution performance. After issuing the query, the DBA examines the planning and execution times. The DBA notes that ASM's execution time outperforms other methods. The DBA now learns about ASM's internals in 4 steps: intra and intertable orderings, per-table statistics estimation, inferring join key distributions, and statistics merging. For intra and intertable orderings, the DBA can view the ordering diagram. Each gray box represents a table in the query. Green boxes indicate non-join key attributes. The blue box represents a primary key, and the red box represents a foreign key. Intratable ordering is shown through a row of an ordering diagram, and intertable ordering is shown through dashed line boxes, representing equivalence groups of join keys. With a hypergraph, the DBA can better understand the join structure and ordering. Clicking on a hyperedge reveals per-table cardinality estimation from autoregressive models. Now, ASM picks samples from a join key distribution for each equivalence group in order. The join key distribution is calculated by aggregating all distributions for the join keys. For example, clicking on the third group IT2.ID shows each equivalent join keys distribution in different colors with 10 real samples. On the right, the aggregated distribution is shown. Below, picked samples and their probabilities are shown. These samples serve as conditions to infer the next group's distributions, and the probabilities will be used in the cardinality estimation. To estimate cardinalities, ASM merges statistics from previous steps. For a simple explanation, consider a join query like this with ordered groups A and B. The statistics are shown on the hypergraph. So, how does ASM estimate cardinalities for the following subqueries? Let's start with the smaller one. As A is the only group in the subquery, probabilities of A for tables 1, 2, and QA are relevant statistics. Now, ASM merges statistics with this resulting formula. Similarly, for 3 tables join, ASM merges relevant statistics. Since A and B are equivalence groups, red-colored statistics are merged. This statistics merging captures the correlation between join keys, resulting in accurate cardinality estimations. With a closer observation, T1 join T2's cardinality is included in the formula. To accelerate the cardinality estimation of larger subqueries, ASM memoizes and reuses the cardinalities following a dynamic programming approach. In the actual demo GUI, the DBA can check each memo entry's estimation formula and the reuse of cardinalities, along with 10 real samples for the issued query. Now the DBA explores the estimation graph, which is our tool for analyzing the impact of cardinality estimates on query plans. Each node corresponds to a subquery, showing the information of its estimated cardinality, subplan chosen by the optimizer, and other rich insights. Since we show such information for every subquery, it offers a huge benefit over existing plan visualization tools such as Dalabo, which only shows the selected query plan. The nodes are grouped in rows based on the number of tables, with the larger subqueries being placed at the top. Each node size represents the actual plan cost, and color represents plan cost errors. Edges correspond to decomposition relationships between subqueries. For example, MIIDX join MI can be decomposed into MI and MIIDX, so there are edges between them. The green path shows the join path selected by ASM, and the blue path shows the join path selected by true cardinalities. Clicking on a node reveals detailed subquery information in tabular form. Below the table, the best estimated plan is shown. This is a plan with the lowest estimated cost from the node. The best estimated plan of the root node then denotes the executed plan. Finally, we introduce the what-if analysis feature. Suppose that the DBA wants to explore whether ASM could have chosen a better plan if the cardinalities of certain subqueries had been accurately predicted. We use the JOB2B query since ASM unfortunately chooses a suboptimal plan. Here, the DBA notes that the costs of the nodes on the chosen path are underestimated. The DBA modifies the chosen path's cardinalities to true values to see the effect. With this little change, the DBA observes that the ASM chooses the optimal path. This analysis gives deep insight into improving the performance of an estimator. This was our demonstration. Thank you.